All right, so at this point we have the real numbers, all the decimals, negatives, positives, small numbers, big numbers, lots of numbers. But, and we can solve um, all the linear stuff, so something times x plus something equals something. You can solve for x, no problem. You can subtract, you can divide, all good. We got answers. We can do lots of, you can solve any kind of power. X to the fifth, for example, equals 19. We can do that. We have the tools. The numbers exist. We know how to compute them. We know how to add them, multiply them, and all that other good stuff, right? That's all done. So are we done? No. Almost. So everything up to now has led to the real numbers. And they're called real because there's a certain sense we feel like we can measure them, we can deal with them. Um, if you have something whose length you're trying to measure, in our minds, it could be any real number. In reality, it's going to be a rational number because we can't measure infinitely precisely, so you're going to stop at some point, right? So, but, mentally, you can say, it's good, it's good. I could have a height of pi inches. Why not? Cool. Um, small, small. The model image of me is pi inches. Anyway, so the next thing we're going to introduce, it's called imaginary because it feels like it doesn't have the same reality as the other numbers. It's a lot of the times it's something that is not the answer. It's a middle step in the answer, and it makes things easier. Now, unfortunately, a lot of that middle step stuff is for stuff that happens later. So there are various calculus stuff that is most easily done, or perhaps only understood by thinking of these complex numbers, these imaginary numbers. There's a certain sense in which these numbers, it's like that's the completion in some sense, even though it seems like it doesn't quite relate to the problem. So, like, there's techniques for approximating one thing with another, and they break down at a certain point, and it's not obvious why it breaks down there. When you look on the complex plane, you can see that if you go around in a circle on there, there's a point on that circle where something bad has happened, and that's affecting the things on the real line. So that's, there's also a lot of the wavy behavior in life, electrical circuits and so forth, quantum mechanics, all of these things, there's a natural role for imaginary numbers to play. In fact, the square root of -1 actually appears directly in the defining equation of quantum mechanics. So, it has a lot of applications, but at this level, it's more about introducing just the idea. So what is the idea? Well, the idea is simply x squared equals -1 has solution I. J for engineers. I'm not kidding. Seriously. Engineers use J. Most other people use I. But I for imaginary, J for imaginary. It's because they use I for something else. So that dominates. Anyway, so we can write I equals square root -1. So that's the mantra, but that doesn't actually make any sense. Square root -1 doesn't really by itself. It's a definition. It's like I want this thing to be -1. So square root of -1, which means I squared equals minus 1. We also have that minus I squared equals minus 1 because squares distribute. So minus 1 squared and I squared equals plus 1 minus 1 equals minus 1. Okay. Now, we can think of a complex number as something of the form, I'm tempted to use A and B, except that'll get confused with the quadratic formula stuff. So then I'm tempted to use U and V, because that's a standard kind of thing, but my U's and my V's look almost the same. So I'm going to go with V and W. So V plus IW, or we could also think of it as VW, so point in the plane. So, you know, we've basically gone from, so these are the natural numbers, right? And then we added minus 1, minus 2, minus 3, and then we added things like 1/2 and 1/4 and these things, oops, sorry, there's 1/2 and there's 1/4. Anyway, and you do that, and then with the, so let's see, that was, this is kind of adding the integers, and then the dot 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 was sort of the rationals, and then the reals, you know, that was the reals, everything on that line. And now comes along the complex plane. So now we've gone two-dimensional in all this world. And so whole new possibilities arise up. And so the point on this plane, say it's VW, and that's our number, right? And so with the square root of minus 1, I, in there, the V plus IW, it's like the V and the W kind of live in two separate worlds in many ways. So like, for example, if I take 2 plus 4I, and I add in, say, minus 1 plus 2I, sorry, let me just write that as 3I so that all the numbers are distinct. It doesn't matter, I just don't want you to try to do some weird matching. So 2 minus 1 is 1, plus 4 plus 3 is I, 7I. They just live in their separate worlds. If I did 13 here, that would be 17 here, right? So they're just separate, which also means that if V plus IW was equal to 0, then that implies that V equals 0 and W equals 0, right? Or if V plus IW is equal to 4, then V equals 4, and W equals 0, right? Like there's this real and imaginary parts. So V is the real part, and W is the imaginary part. So that's, you know, just kind of basic. Now there's multiplication to do. Well, we just do what we think we would do, right? So what would that be? That would be 3 plus, say, 4I, and 5 plus 2I, and we use our good old distributive rule. As I like to do, I will write that as a box, 3 and 4I, and 5 and 2I, 15, 3 times 2I, it's going to be 6I. So you just multiply it all together. 4I times 5 is 20I, and then 4 times 2 is 8, and then we have 8I squared. But I squared is equal to minus 1, and so all of this is equal to 15 plus 6I plus 20I minus 8. or it's 7 plus 26i. All right, so that's nice. In general, the formula is, I'll just use a AB here. It's VAA minus WB plus IAW plus BV, and that's it, right? So that's cool. Now, division is always an interesting thing with complex numbers. But basically, we just need to care about reciprocals because division is just multiplication by reciprocals. So let's say that we wanted to do 1 over 3 plus 4i. So I have no idea what that is, but I can use this little trick. So I do the complex conjugate. That's a fancy word for saying change the sign in front of the I term. And then do the same on the top so that I'm multiplying by 1. Still the same rules. The same thing on top and the bottom means they cancel, and you get 1, right? And you just multiply the top and bottom when you multiply two fractions together, all the same kind of stuff. So we get 3 minus 4i on the top. And the bottom, well, here's our little box, 3, 4i, 3 minus 4i. We've got a 9. We got minus 12i, got plus 12i, and then we have minus 4 times 4 is minus 16, I squared minus 1, so that's a plus, so that's a 16. So those cancel, and that becomes a 25, so it's 25, equal to 3 minus 4i over 25. Okay. And if you were to graph this in the complex plane, so the original thing was 3 over this way and 4 over this way, so it's like this. And the length here is 5. That's because it's 3 and 4. This is not drawn all that terribly well. And then what is 3 minus 4i? Well, that's going to be here, here, and then it's kind of like, so that this length is, well, so that's a minus 5. I think it's 1/5. Yeah. So basically, this angle here, theta, is going to be the same angle here, just in the counterclockwise. And then this length here, 5, is the reciprocal of this one, 1/5. So that when you multiply them together, you'll get 1. And so multiplication ends up, the complex being add the angles and multiply the magnitudes. So that's the angle, and that's the magnitude. All right. But anyway, there's just this little algebra. And maybe we'll explore in GeoGebra a bit more of these kind of cool things. Anyway, so this is complex numbers. Division, subtraction is just what you think. Negate both of the numbers, so 2 plus 3i minus 5 plus 2i is just going to be a minus 5, so it's minus 3 minus 2i, so plus I. That's it. All right. Easy peasy. Taking integer powers of things ain't too bad. So 2 plus 3i squared, for example. Oops. I did that. Again, it's just going to be our little box formulas. So that's 4, 12L, 12i, 12i, and 3i squared, or minus 9. So we get minus 5 plus 24i. Okay. Notice, it's kind of important, that even though the original thing had no negative signs, when we squared it, we ended up with a negative sign, right? Why? Because I squared is minus 1. So if the I term has a large enough thing, that negative will dominate and you get a negative.